The video recording you've seen, or just the frequency response? Yes?
Yes.
The both plot. Okay, perfect. So today's class, we'll start a different topic, a very important topic, the core topic of this module, which is filters design. It will rely slightly on what we've learned in the last 2 weeks, which are the transfer function and the both plots, how we can plot the frequency response. In today's class, we're going to have an introduction to filters, just understand the concept of a filter. We're going to learn about the different types of filters and their practical implementation. I'll give you some examples of them, and then we're going to look at how we can build higher order filters and how we can analyze a circuit to judge it on its filtration behavior. But before I start all of this, I just want to ask you, those who are joining online, you can join as well. What does filter mean to you? When you hear the word filter, what is the first thing that comes to mind? Generally, filter. What is filter?
Clear something.
To clear something. Okay. Anything else?
For example, if there is many points,
Mm-hmm.
I want some points, so I can filter that.
Okay, you want to remove something, right? So whether we're dealing with a car filter, whether we're dealing with a water filter, the concept of filter is to clarify or to isolate unwanted parts, right? Usually, when you want to clarify or clear something or remove something, for example, if I take water filter or oil filter, for example, the clarification is based on the size of the thing that you want to remove, right? But when we are clearing or filtering signals, what are we clearing out? When you're clearing signals, you're isolating or you're removing signals based on their frequency. Okay? So this is how a filter circuit works. It's a frequency selector filter circuit. The filter is a frequency. Based on the frequency, you get to select. How do you select? It depends on what type of filter are you implementing. So when we're talking about a filter circuit in signal processing, we're talking about a specific frequency selection. Either we want to pass specific set of frequencies or we want to eliminate or remove a specific set of frequencies. And based on that definition, we have 4 types of filter. So based on what are you passing and what are you blocking, we have 4 different types of filter. The first type or the first 2 types will be the building blocks to the other 2. The first type is the low pass filter. So as the name indicates, low pass filter, it's a filter circuit that will allow lower frequencies to pass through it and higher frequencies will be blocked. So what does that mean? Before we go to the frequency response, let's say that I have this combination of signals and I'm plotting them in frequency domain. So basically what I'm plotting is frequency versus gain. And let's say that I have 3 different signals. Let's say we have a signal at frequency omega 1, another at frequency omega 2, and a third at frequency omega 3. 3 different signals, 3 different frequencies, all of which, so this is my input. And let's say that I have applied this input to a low pass filter. What do you suspect the output would look like if I say that this is a low pass filter with a cutoff frequency that is right here? Let's say call this omega C, the cutoff frequency. So what do you suspect we'll see at the output side of the filter? If this is the input, what do you suspect will be the output? Now, because it's a low pass filter, frequencies lower than the cutoff frequency will pass. Frequencies higher than the cutoff frequency will be blocked. So if this is your cutoff frequency at the green cross, this means anything prior to that, which means lower frequency, will appear at the output. Anything higher than that will be blocked, which means that I will see the signal with the frequency omega 1. I will see the signal with the frequency omega 2. How about omega 3? Omega 3, is it higher or lower than omega C, the cutoff frequency? Higher, right? Not lower, higher. So this is our axis. We're starting from 0 onwards. This is greater than omega C, which means it's outside the window, will be blocked. So you will only see the signals omega 1 and omega 2 at the output of the filter. We call this a low pass filter. Or in other words, this was the pass band of the filter between 0 and the cutoff frequency omega C. So anything that's within the pass band will pass. Anything within the stop band higher than omega C will be blocked. So we call this a low pass filter because lower frequencies pass while higher frequencies are blocked. And what is the judging point? Omega C, the cutoff frequency. Okay. The opposite to that is the high pass filter. It's the exact opposite. You have the same cutoff concept, but anything lower than the cutoff is eliminated. Anything higher than the cutoff frequency will be passed. So let's say that I have a high pass filter with the exact same cutoff frequency omega C. And we apply the same input to it. What do you think will appear at the output? If it has the exact same frequency, this one, omega C. Only the signal omega 3 will appear, right? Because this is the pass band of the high pass filter, which means I'm only going to be able to view omega 3. Omega 2 and omega 1 are in the stop band. Clear? So we have high pass filter, we have low pass filter, and then we have another two, which are the band pass and band stop. So band pass filter, as the name indicates, instead of just single break cut frequency, where whether you're higher or lower, you get to pass, we have a range. We want frequencies between omega 1 and omega 2 to pass. Anything outside that range, whether it's higher than omega 2 or lower than omega 1, we want it to be blocked. So this is called the band pass because we have a specific band that we want to pass, which is between the two cutoff frequencies, omega C1 and omega C2. The final fourth type of filter is the band stop, and it's the exact opposite of band pass. Instead of saying that I want a specific band to pass, I want a specific band to be eliminated. So I want between omega C1 and omega C2 exactly to be blocked. Everything else passed, but except for this particular range. Now, why do you need this type of circuit? Before we go to the implementation and the circuit design of these circuits, where do you think filters will become handy and very good application? Have you heard of, let's say, radio stations? When you listen to the radio in your car, do you notice that each radio station has a specific frequency? And when you change the station, whether it's a knob in very old days or a button, what you're doing is you're actually applying a band pass filter that gets or picks up the exact band of your radio station. Radio walkie-talkies. In, for example, law enforcement, they use radio. They don't use regular hyper channels. So they want to pick up a specific audio, right? So we use band pass filter for these applications. An example of band stop filter is music or audio enhancement. Let's say you've recorded an audio, it's really clear, you were recording a conversation between two people, and then there was a noise, a street noise, or a barking dog, or a door opening and closing, and you want to remove that noise from your recording. So you'll choose the band stop filter to block only the frequency that you're not interested in. Make sense? So filters have a lot of these, just examples, but they have so many other applications. In communication, in system design, there are so many applications for filters in circuit design. Now, if you notice all four filters that I've showed you now, all these frequency responses, so this figure where we plot frequency versus gain is called the frequency response. In all these figures, you'll notice that these are ideal filters. What makes them ideal is two things. Step one is that if you look at the pass band in all four types of filter, what do you notice about the pass band gain? It's a steady line, right? Whether at the beginning of the pass band or you're at the end of the pass band, your gain is the same, steady and stable and a fixed value, right? For all filters. The other thing you notice is that the transition from pass band to stop band. What do you notice about it? From here to here. It's a very sharp transition, right? At one frequency, you're at the pass band. Immediately after, you drop to zero gain. You're in the block stop band, right? So this sharp behavior of having a stable gain, of having a sharp transition, these are ideal characteristics, which we refer to as the brick wall. They look like a wall. Line and a sharp transition from high to low. These brick wall characteristics are ideal, which means realistically, these are ideal if you're simulating or something, but when you build an actual circuit, it is impossible to have such behavior, an ideal square transition. Realistically, what happens is instead of, let's say that this is the ideal, realistically, what you'll be actually looking at is some transient behavior, ripple effect. Just a moment. Use a different color. It will ripple a little bit, it will stabilize a little bit, it will gradually transition from pass band to stop band. So these ideal characteristics, they don't exist in real life. In real life, you have a little ripple, which means that the gain is not stable. The gain will be fluctuating slightly. And the transition from the pass to the stop happens gradually. It doesn't happen immediately, abruptly. Now, as a designer, usually your goal is to get as close as possible to the ideal, which means you want to minimize this fluctuation, the ripple effect. You want to enhance this transition to make it a little bit sharper, right? However, solutions to make the gain stable tends to make the transition slower. Solutions that make this transition sharper tends to create a rippled gain. So it becomes a trade-off. It becomes of getting to that exact spot that where you get acceptable ripple and acceptable transition roll-off. Does that make sense? We will see how that applies in design and mathematically in a moment, but just let's get the concept. So these are ideal filters. Now, how do we build a filter circuit? There are two options. You can either build a passive filter or an active filter. The only difference between passive and active is the presence of active components. What does that mean? When I want to build a filter, I have to choose either resistors and capacitors and inductors. I have to choose from these components to build my filter. Resistor, capacitor, inductors. Okay? We'll see in a moment how we build them. But that's it. We don't use any other elements, which means that if your input signal was 1 volt, your output signal can never be more than 1 volts. It could be slightly less, but it can never exceed 1 volts, right? The only difference here, so it's either 1 or less. But when you use an active filter, you add to the standard components of resistor, capacitor, and inductor an operational amplifier with the purpose of enhancing the signal, which means that if your input is 1 volt, your output could be 5 because you're boosting the signal with an amplifier. That's the only difference between passive and active. So the filtration process, how you can create a circuit that will eliminate certain frequencies, is solely based on resistors, capacitors, and inductors. The amplifiers don't do filtration. They don't block frequencies. They only enhance the amplitude of the pass band. Clear? So instead of your pass band perhaps looking like this, it could be more like this with a higher amplitude. That's all. And that's the only difference between a passive and an active filter. So for example, let's go to, let me create an example. Let's look at this circuit over here. If I say that this circuit actually implements a filter, can you tell me whether it's passive or active? Just by looking at it? Now we've mentioned that the only difference is
Active.
that active filters have amplifiers. So is it passive or active? Can you come again online?
It's active.
Now let's go back to the definition. We said active filters have operational amplifiers of amps. So does this circuit have an operational amplifier? No. Just all you have to do is just look at it. Is there an operational amplifier? Then it's active. If it doesn't have, then it's a passive circuit. This is a passive circuit. Now the next step would be, can we tell what type of filter this circuit implements in terms of, is it low pass, is it high pass, is it band pass, or is it band stop? And this will be assessed in your final exam. You'll be given a circuit and you'll be asked to decide what type of filter it implements. So all you have to do is first look at what is the transfer function. What is the relationship between the output and the input? So we call that the transfer function, h of s. We studied that in the Laplace transform the week before last, which is the output, which in my case is V2, divided by the input, V1. Are we following? Output over input. And we know from voltage divider rule that this is basically the capacitor impedance divided by the total impedance, correct? Are we following? Capacitor impedance is 1 over CS. Total impedance, because they're connected in series, will be equal to R plus 1 over CS. What we will do next is unify the denominator. So the common denominator will be CS. This R becomes R times CS plus 1. Are we following? These two counter each other out. So therefore, my transfer function h of s is equal to 1 divided by R CS plus 1. Do you agree with that? So now we have a transfer function. We still don't know what type of filter it implements. We only have the transfer function. So in order to tell what type of filter it implements, we have to plot the frequency response. So from last week, we said that to plot the frequency response, you have to first get the transfer function. Second, identify what are the elements of this transfer function. And when I say elements, I mean, are there constants, zeros, or poles? And then plot them. So all we want to do is plot the both plot of this transfer function. So let's look at this function here. Do we have zeros? Zeros, let me remind you, are values of s that will make h of s equal 0. قيم s اللي هتخلي البسط وبالتالي الدالة تساوي صفر. هل في أي قيمة ل s هتخلي البسط صفر؟
ماينس 1.
نو. نو. نتكلم عن البسط، احنا معنا المقام. هل في أي قيمة ل s ممكن تحول البسط لصفر؟ نو، لأنه أصلا البسط قيمته واحد ثابتة. There's no. So we don't have zeros. Okay? This transfer function doesn't have zeros. Do we have poles? قيم ل s تخلي المقام صفر. Poles are values of s that makes the denominator equals 0.
minus 1.
Are you sure? So we want the denominator, which is RCS plus 1, to be equal to 0. Which means that RCS is equal to minus 1. Which means that S is equal to minus 1 over RC. So when S is equal to negative 1 over RC, then the denominator will be 0, right? So we have a pole at 1 over RC. And you'll notice I ignore this negative sign because S here represents J omega, and omega is a frequency. And natural real frequencies don't have negative values. So I'll just take the magnitude, the value, okay? So we have a pole at 1 over RC. So now we establish there are no constants, there are no zeros, there is a single pole. How do we plot a single pole in both plot, which is the linear approximation? You plot frequency versus gain in decibels. And here we have a one pole at which value? At 1 over RC. So I'm going to look at where is 1 over RC is. Let's assume it's there. And the way you plot a pole is that from the beginning until the point of 1 over RC, the gain is flat, 0. At RC, it will start to drop gradually. We've already been through this last week, but please ask any question if you have right now, okay? So this is a rule of how we plot poles, that we decide what is the value of the pole. And then from that point, which we call the break frequency, so 1 over RC is called the break frequency, we'll have a constant drop of gain. So this is gain in decibels. And in decibels, 0 decibel means 1 in actual numbers. Which means that if you look at this signal in regular gain, not in decibels, it has a stable amplitude at 1, which starts to drop at 1 over RC frequency. Alaykum salam. Clear? So if you look at this plot, what type of filter does this plot implements? If you look at this frequency response, where we do have a gain all the way up to 1 over RC, and then our gain starts to gradually decrease. What type of filter is that? Low pass, high pass, band pass, or mass stop?
Low.
Low pass, right? Because you know the ideal characteristics of a low pass filter is like this. So this looks like a low pass with a less than ideal transition from pass band to stop band. So this circuit, where the input is V1 and the output is V2, is an actually low pass passive filter. Make sense? And where did we get that from? The entire thing is based on the transfer function. When we plotted the frequency response, this is what we have. So we had the gain, and this was the gain value. We got the gain in decibels, we got the phase. When we plotted the gain, this is what we have. Exactly what we did over here. Right? So this here is a passive low-pass filter. Now, if I take this exact same circuit of the low-pass filter, and instead of saying that the output is V2, the voltage of the capacitor, what if I say that the output is VR, the voltage across the resistor? Do you think it will still be a passive low-pass filter, or will be something else? Since you've changed the output, the circuit behavior will change. Not the circuit, but the reading value will change, right? So let's do a test for that. Let's say that we have the exact same circuit, but this time I'm taking my output from the resistor, not from the capacitor. So if I try to find the transfer function, H of S is equal to V2 over V1. Applying the voltage divider rule, it would be ZR over Z total. ZR is equal to R. Z total is equal to 1 over CS plus R. I will repeat the same process I did earlier just to simplify it. So I'll simplify by unifying the denominator. نوحد مقامات المقام. So we'll have 1 plus R C S, right? This CS will go here. It becomes RCS over 1 plus RCS. Make sense so far? So this is my transfer function. Now, based on this transfer function, let's try and plot the both plot, the frequency response. So now let's again try to find the elements. Do we have zeros, values of S that will make the numerator 0? Yes, which is 0. Perfect. So we have 0 at origin. Origin means at point 0. Do we have poles, values of S that will make the denominator equal to 0?
-1.
Again minus 1. قيم S اللي هتخلي المقام ده صفر كم؟ 1 plus
1 over R.
1 over RC is equal to 0. It's the exact same denominator from the previous examples. Huh? So we have a pole at 1 over RC, correct? Let's plot them. We have the frequency, we have the gain in decibels. Let's plot the 0 at the origin. Now, previously you said that zeros and poles, the way we plot them is exactly the same, except at the break frequency, zeros will be increasing in gain. Poles will be decreasing in gain. But we have one special case, which is if the value is at 0 at the origin. Instead of saying that it will increase at the break frequency, I go and find point omega equals 1. And it will increase with a straight line from point omega equals 1. So this represents this 0 at the origin. Okay? with an increment of 20 decibels per decade. What does that mean? It means that when I go to point 10, this is 0. Here it will be 20. When I go to 100, it will be 40. So every decibel, every 10 power, it will increase by 20 in gain. So this is just the slope, how the tilt of this line is represented. And the tilt of the line is very important because the tilt of the line, as we'll see in a moment, tells you how accurate or how close it is to the ideal brick wall. So this is the 0. Now let's plot the pole, a pole at 1 over RC. So I'll try to say, for example, let's say 1 over RC is here. So the pole will be from start until 0.1 over RC, there is no gain. And then at 1 point RC, what happens? Do we increase or drop when it's a pole? What will happen at the break frequency when we're plotting a pole? And just revise. This is just a quick revision of how we plot these board plots. This plot is called board plot. The rule is step 1, we define our constants, poles and zeros based on the equation. We find what values of S will make the numerator 0. يعني نبحث عن قيم S رح تخلي البسط صفر نسميها zeros. نبحث عن قيم S رح تخلي المقام صفر نسميها poles. نبحث إذا في ثوابت، يعني إذا الدالة كلها مثلا مضروبة في رقم نسميه constant. الخطوة اللي بعدها we start to plot each of these elements. نبدأ نرسم كل زيرو على حدة، كل pole على حدة، كل constant على حدة. الرول للبود بلوت بنستخدم حاجه اسمها linear approximation اللي هي التقريب الخطي. يعني this is not ideal بس تقريب just to see what will the response be. The rule is انه قيمه البول او الزيرو اسمها البريك فريكونسي. اذا كان زيرو اللي هو قيم البسط بيكون في زياده، اذا كان بول بيكون في نقصان. اوكي، هلا احنا want to plot a pole. البريك فريكونسي is 1 over RC. هل حيكون زياده او نقصان بعد البريك فريكونسي؟ نقصان، لانه يعني نربط المقام الاسفل بنقصان، البسط الاعلى بالزياده. ف here we'll have a drop. Now if I ask you of the order of this equation 1 over RCS، دي معادله من الدرجه الكم؟ الاولى، الثانيه؟ what is the order؟ الاوردر معتمد على الهايست باور اوف اس. الاولى صح. So if it's first order الريت of change او معدل ميل الخط بيكون 20. So here we'll have negative 20 decibels per decade. إذا كانت من الدرجة الثانية الميل حيكون 40. 40 معناه حيكون أكثر حدة. يعني if this is 20, 40 will most likely look like this. It will be sharper. The higher the order, the sharper the transition, which means with higher order we'll have closer brick wall characteristics. يعني حيكون أقرب للشكل المثالي. Okay? So let's keep it that way. Now we're dealing with a first order. So we've plotted each and every element separately. الخطوة الأخيرة احنا حاليا رسمنا فقط البول منفصلة، الزيرو منفصلة، الكونست منفصلة. الخطوة الأخيرة الآن احنا عايزين نشوف الدائرة كاملة مش الكومبوننتس، نجمع القراءات دي مع بعض في رسم واحد. How do we do that? By identifying just a moment. Okay, points of change. فهنا من البداية إلى البوينت 1 over RC، من البداية إلى النقطة دي 1 over RC. The only contribution is the blue line صح؟ So this is the only contribution. And then we get to 0.1 over RC, what happens? We have the blue line and the red line. The blue line is respective to a 0 with 20 decibels per decade increase. And the red line is negative 20 decibel decrease. فإحنا عندنا زيادة بمعدل 20 ونقصان بمعدل 20. إذا معدل التغير الكلي كم؟ عندنا موجب 20 وسالب 20. 0. إذا at this point it will not change. It will be a steady line. والخط مستقيم. Okay. فإذا when I plot this, this is what it looks like. Just to make it clear, يعني if this is omega and this is gain, it goes this way and then it stabilizes, right? This is pass band. This is negative gain, very attenuated. Then what type of filter is this circuit? Low pass, high pass? High pass, right? So the same circuit, if you take the output from the capacitor, you'll get low pass filter. If you take the output from the resistor, you'll have high pass filter, which is exactly what we have here. Where is it? High pass passive filter. Based on the transfer function of the circuit over here, which we just calculated. Okay? طيب. Now we know how to build a high pass and how to build a low pass filter. At the beginning, I told you we have 4 types: high pass, low pass, band pass, and band stop. The high and low are the building blocks that we use to build the band pass and band stop. How so? Let's say that I want to build a band pass filter. Just a quick reminder, a band pass filter is a filter that will allow only a specific range to pass between cutoff frequency 1 and cutoff frequency 2. And everything else will be blocked, right? So if I want to create this type of filter, we can reimagine that basically we have a low pass filter with a cutoff frequency omega C2, which means that this is my pass band for this low pass filter. And then I have a high pass filter with a cutoff frequency omega C1. And they overlap between C1 and C2. So if you plot, for example, let's say I have this signal and we have 3 frequency components, 1, 2, and 3. And let's say that I have a low pass filter connected in series with a high pass filter. Okay? Let's say that the cutoff frequency of the low pass filter is omega L, and omega L is here. Okay? And let's say that the cutoff frequency of the high pass filter is omega H, omega high pass, and omega H is here. Now, if you apply this signal here as an input, what will I see here after the low pass filter? So I've inputted omega 1, omega 2, omega 3 combination to the input. What will I see at the first stage after the low pass filter? Which signals will be visible? So we said that this is the cutoff frequency of the low pass filter, right? Which means this is my pass band. So what do I see? And also omega 1, right? You'll see both of them, omega 1 and omega 2. So this is what you'll see at the first stage. You'll see omega 1 and omega 2. This will be the input to the high pass, right? So what would you see after the second stage here? What will I see? Because this here will be considered input to the high pass filter. And the high pass filter frequency is here, between them, which means higher than it will pass, lower than it will be blocked. So what do I see at the output?
Omega 3.
Only omega 2, only the middle one, right? Because this is the pass band, this is the sub band, right? Omega 1 is eliminated. So the only thing left is omega 2. Does that make sense? Clear-ish? You know what?
Why omega 1 is sensitive?
Because if you apply 2 signals, omega 1 and omega 2, which is what we have, and your cutoff frequency is here. And this is a high pass filter, which means anything below the cutoff frequency is eliminated, anything above the cutoff frequency is passed. So anything below the cutoff frequency will be gone, will be filtered out. Does that make sense? Let's start from the beginning. Let's start with an empty. Let's say that this is my initial signal. We have 3 different frequency components. We have omega 1, omega 2, omega 3. This is gain, this is frequency and radius, okay? This goes as input to my first low pass filter. What would be the output of the low pass filter? Low pass filter has cutoff frequency here, omega low, with the cutoff frequency omega low. So this is the pass band of the cutoff of the low pass filter, right? Which means what will happen to omega 3? It will be blocked. So the output that you'll see would be only one
This will omega 1 and 2 when capacitor charge or only after charge.
after charging.
We decide we have capacitor and resistor, right?
Yes, so okay, perfect. So it will be resistor, capacitor, V1, this is your input, this is your output,
The omega
V
1
out.
and 2, and it's when the capacitor charge.
After the capacitor charges, after it works. This is called the, so the time where the capacitor charge is called the transient behavior, initially. Initially, the first few seconds or the transient behavior of the circuit is not accurate. We don't rely on it. We rely on the steady state behavior. Okay? So now we got this. Based on this, the output of this low pass filter is now used as an input to a high pass filter. And for the high pass filter, let's assume that, let's make it color coded, let's make it blue. So let's say that this is now an input to a high pass filter with a cutoff frequency omega h. And this is where omega h is, which means any frequency above omega h will be a pass band, anything below it will be blocked. So what do you expect to see here? Only omega 2, right? So effectively what we have created is a band pass filter that will only allow the band where we have omega 2 or the band between omega high and omega low to pass, right? So this is how we build a band pass filter, by cascading. Cascading means connecting two filters in series. And you can actually test to see that this is actually a band pass filter by checking the transfer function V2 over V1. Let's say that this is an intermediate voltage Vx. V2 over V1 is equal to what? V2 over Vx times Vx over V1. Agreed? Yeah? Okay. What is V2 over Vx? Here. This is a high pass filter, right? If the input is Vx, the output is V2. And we already previously, in the previous example, established that for a high pass filter, the transfer function is RCS divided by 1 plus RCS. We already calculated this. Moving on to this first stage, this is a low pass filter. This is a high pass filter. We already know Vx over V1, which is the output divided by the input of a low pass filter, which is equal to 1 over 1 plus RCS, right? Let's just add values. This was R2C2, R2C2, R1C1, right? So the transfer function is R2C2S divided by 1 plus R2C2S times 1 plus R1C1S, right? Now, if you look at this transfer function, can we define its components? Do we have zeros? Values of S to make the numerator 0, which is 0 at 0, 0 at origin, perfect. Do we have poles? Values of S to make the denominator 0. Minus 1, perfect. So 1 over
R1,
R1C1. Any other poles we have? We have two values.
poles.
We have So either the first term is 0 or the second term is 0. So the second term would be a pole at 1 over R2 C2, right? Let's plot omega and let's use a. Okay. So we have omega, we have gain in decibels. We can start with the 0 at the origin. We said it's a special case of gradual increment, right? And then we have the pole at okay, we have the pole at 1 over R1 C1, which is basically this. And then we have the pole, it's the exact same thing we plotted earlier. 1 over R2 C2, which is this. Is it clear so far what we're doing? Next step would be to plot the total both plot. So just start to add them. From the beginning all the way until 1 over R1 C1, what are the contributions that we have? Only the contribution of the 0, the red line, right? So from the beginning all the way here, we only have one line. Between 1 over R1 C1 and 1 over R2 C2, what do we have? We have the red line and the green line, right? An increment of 20, a decrement of 20. So the total change is what? We have one line increasing and one line decreasing. So it will be 0, which means that there will be no change. Whatever value we reached, we will maintain. And then we get to 1 over R1 C1, and then what happens there? You have the red line, positive 20. We have the blue pole, negative 20. We have the green pole, another negative 20. So positive 20, negative 40. So what would be the rate of change? Negative 20. So we'll start to decrease. So if I'm to just plot only the final combination, here we have cutoff 1, which is based on, cutoff 2, which is based on R2C2, cutoff 1, which is based on R1C1, and it looks something like this, right? Goes up, stabilizes, drop down, which looks like what type of filter? Low pass, high pass, band pass, band stop. Band pass. So to build a band pass filter, all you have to do is connect a low pass filter and a high pass filter in series, and that's it. Make sense? Okay, so this would be the gain that we get, which we already established, and it will look something like that. Okay, so now we've looked into that. How do you think we will be able to build a band stop filter using a low pass and a high pass filter? We learned how to build a band pass filter by combining them in series. And it doesn't matter which one goes first, whether it's the low pass first or the high pass first, it doesn't matter. At the end, you'll end up with the same result. What if I want the band stop? And just to remind you, the band stop looks like this. These are my pass bands, and between omega C1 and omega C2, you have your block or stop band. How do you think we can build this with a low pass and a high pass filter? If you look closely, you'll notice that this bit is a low pass filter, right? And this bit is a high pass filter. So basically what you want is to have a low pass filter independently and a high pass filter, and then you want to figure out a way to add them. So you not connect them in series, connect them in parallel, and then combine them. This addition is very important. And how you can perform this addition? Using a circuit. Are we familiar with the adder circuit? So you just build an adder, you add the outputs of the low pass filter and the high pass filter, and you end up with a band stop filter. Clear? Of course, there is the requirement that omega C1 must be less than omega C2. right? So what will happen if omega C1 is not less than omega C2? They will overlap, which means your output will be an all-pass filter. There will not be any block band. Here. Now, when you're combining circuits, cascading them or connecting them in series, remember that you always have to include a buffer. This plot over here is just an ideal representation. They don't connect directly ever like this. You have to create a buffer. Why? Because the V input here will have some drop across R1. So by the time it gets here, it will most likely be attenuated. So just to enhance that and ensure that your filter operates properly, you need to add this buffer to boost your voltage of your signal and to enhance it before it goes to the second stage. Whenever you have a circuit with multiple stages, you might need to add boosters in between just to enhance the strength of the signal. Clear? Because if you start with 5 volt, at some point this 5 volt might drop down to 2.5 volts. And then it will not be sufficient perhaps to activate or to charge the capacitor C2 for it to function properly. As he asked, will the capacitor be fully charged? So that's why we need the booster. Clear? Okay. Now, up till this point, you'll notice that all the filters that we looked at, all the implementations were first order, right? And first order, we said will have the roll off or the transition between high and low of 20 decibels per decade, right? And we said that 20 decibels per decade could look something like this, a gradual transition between pass band and stop band. But 40 decibels will be a little bit sharper. 60 decibels, which are of third order, will be even more sharper. 80 decibel, which is fourth order filter, will be even sharper. And the higher the order, the sharper the transition, which means you're getting closer to that brick wall ideal characteristics. So how do we build a second, third, or higher order filter? One easy way to do it, there are other ways where you can use a bit complicated circuit, different topology, but one of the easiest way to do it, to take a first order filter, connect it with another first order filter, this is basically a second order filter. If you cascade them, connect them to each other. For example, let's look at this. This is a second order low pass filter. Why is it second order? Let's look at the transfer function. This one has the transfer function of 1 over SCR plus 1, multiplied by the transfer function of the second, which is 1 over SCR plus 1, right? The transfer function of the first stage multiplied by the transfer function of the second stage, which means that your total transfer function is 1 over SCR plus 1 squared. So just by connecting them in series, you have increased the order of your filter. You can have a third order by adding a third stage, fourth, fifth. The more you add, the higher the order, the closer to the ideal. However, you'll have double the number of components, which means you'll double the energy consumption. You'll increase the delay propagation from input to output because now it has to go through more components. You'll increase the losses because there will be more drop, right? So you'll get more ideal, but there is a price in terms of delay, footstep of the circuit, which means it will be larger, double the size, number of components, energy consumption. So it's always a trade-off. Do we want that ideal characteristic? But for example, you're designing a consumer electronic, which we'll explain in a moment, the sound to light filter, which is your group project. You want to create something lightweight, portable that you can carry around. So if you increase the size of the filter with that method, the size of your device will increase, right? The battery life will decrease because you're using more energy. So it's a trade-off. As a designer engineer, you have to just sit down and decide which way is the best that suits my requirement or my application. Okay? Is it more important to have the ideal characteristics? Is it more important to have the lower energy consumption and so on? Clear? It is always based on the application. Here we also have another application or another example of a high-pass filter. It's the exact same process. You just cascade them. Is it clear? Any questions so far? All good? Online, do you have a question?
No, miss.
Are we ready for an example? Okay, so this example has 3 different problems. It says find, considering that the values of L, C, and R as shown, You're asked to find the three transfer functions when the output is VL, when the output is VC, and when the output is VR. I'm going to do one with them, one of them with you, and I'm going to leave the other two for you to practice. So which one would you like to start with? The output as VL, as VC, or as VR? VR? VL, okay. We'll test with VL. We'll do one, you have to do the other two, and then based on that, you have to decide what type of filter, because the same circuit can have different types, as we've seen. If your output is from R, it's a high pass. If it's from C, it's a low pass. Now we're going to see from L. So we have to do two things. Determine the transfer function and which type of filter it implements. So we have to decide then based on that what filter we have. So let's look at it. Let me just write the values. 1059 micro. Okay. So R is equal to 10 ohms. C is 159 farad. L is 159 microhenry. So what I want to do is I want to find the transfer function h of s, which is VL over Vs, right? We're going to use voltage divider rule, which means it will be ZL over Z total, right? ZL is LS. Z total is ZL plus ZC plus ZR, so it will be LS plus 1 over CS plus R. Okay? Now we're going to simplify the denominator. هنوحد المقامات في المقام. المقام المشترك, the new common denominator will be CS. LS becomes L C S squared. 1 is the 1, no change. R becomes R C S, right? And this CS can go here. So it becomes CLS squared divided by, and let me rearrange it as a quadratic expression. So with the highest power of S, LCS squared plus RCS plus 1. Correct? Now just to make my life easier, I want the denominator المقام يكون an ideal quadratic expression. So I want to get rid of this LC, just so it will look like S squared plus S times a number plus a number. To get rid of this LC, I will multiply by LC and divide each term by LC. Okay? These two cancel each other out. These two cancel each other out. The C and the C cancel each other out. What I am left with is S squared divided by S squared plus R over L S plus 1 over LC. Are we good? This is part 1 of the question done. Find the transfer function. This is the transfer function. Correct? Now all I have to do is just substitute values. So we can say that h of s is equal to s squared divided by s squared plus r, which is 10, L, which is 159, micro is 10 power minus 6, s plus 1 over 159 times 10 power minus 6 squared, because both L and C have the same value, 159 times 10 power minus 6. Are we following? Yeah? Which will be equal to what? Which is equal to s squared divided by s squared plus 62.8 times 10 power 3s plus 39.5 times 10 power 6. Okay? We did the calculation at earlier class. So we have the transfer function, correct? If I look at the denominator, can I factorize it? So my transfer function will be in the form of s squared divided by s plus a number, let's call it a, times s plus a number, let's call it b. Is it possible? Can find a and b using the calculator? Factorizable, right? So once you get this, can I then identify poles, zeros, constants of this transfer function? Okay, let's look at them. Do we have constants? Yes? What is the constant? Is this function multiplied by a number or by a factor? Mafi. If it was 3s squared times something, we could say, but there's no factors. Okay. Do we have zeros, values of s to make the numerator 0? Which is, if s is equal to it, s equals 0. 0 and s is 0, right? So how many zeros do we have? 1 or 2? 2, because it's s squared. 2 identical roots, right? So we have zeros, 2 of them at origin. Do we have poles, values of s that will make the denominator 0? If s is minus a, or if s is minus b, right? But a and b are the root of our original equation. So a pole at a and the second pole at b.
Yes.
Do you agree with that? The value is minus, but the magnitude, القيمة, and we take always القيمة المطلقة ليه? Because I'm using these values to plot a real frequency and there are no real negative frequencies. Make sense? Okay, now we can plot, right? Now we can plot. Let's just put it here. This is omega. This is gain. We set a 0 as at the origin as a straight line at 1, right? A pole at A and a pole at B. So let's plot. This is 1 at A, the decrease, and 1 at B with the decrease. Now, the pole at A and the pole at B are all from first order expressions, right? Which means both of them are negative 20 decibels per decade. Negative 20 decibels per decade. But the 0 is from a squared, right? And we said basically you have 2 zeros at the origin, right? Which means that the rate of change here is 40 decibels per decade increase, right? It has a higher increase. Okay, keeping that in mind, now let's add things together. So from the beginning all the way to point A, the only contribution is coming from this red line, right? Let me use a thicker line. Right? And then at A, what happens? We have an increase of 40 decibels and a decrease of 20 decibels. So what happens? Increase slightly, right? In 20 decibels, not as sharp as the 40. And then what will happen at B? We have a decrease of 40 decibel, an increase of 40 decibel. Straight line. So to look, if I am plotting it in an isolated plot, increase, increase, stop. So what type of filter does it implement? Which one is that? Low pass or high pass? High pass. So when the output is from VL, what we have is a high pass filter based on this transfer function. So can you repeat the exact same process for the capacitor and the resistor? Yeah? Any questions up to this point? Online, do we have a question? Okay. So with that, let me stop the recording.